So the sample use case is sending data over RS-485. And this maybe will also give you some introduction to our communication systems if you haven't seen that before. So what you need to know is you have sort of two outputs from, like, physically that you care about, like physically two outputs on the chip or microcontroller or whatever. One is you have UART, which is just a serial connection. Writing to it sends data, reading from it means you're waiting for data to come in. Okay? The other thing is sort of a direction. So that is just an output. It can be either 1 or 0. If it's 1, it means that you're sending data. If it's 0, it means that you're receiving data. How you usually operate these systems, and the reason why you have that is because the actual communication link, like the cable between the two systems, only carries data in one direction at a time. So usually what will happen is that both things at either end will have it in receive mode, and then if they need to send, they'll turn it on to transmit. So they'll flip direction to 1, then they'll send whatever they need, and then they'll flip it back to receive, and then the other one will have received that because it was in receive mode. It'll process it, do whatever it needs to do, then flip itself into transmit, send data, flip itself back into receive, and it goes back and forth as long as there's data that needs to be sent back and forth. The naive way of controlling this would be, like, let's say I have 4 bytes that I need to send. So direction equals 1, then, again, this is just kind of rough pseudocode. Maybe UART dot send data direction equals 0. There's 2 reasons this won't work. One of them is that so between your interface and the actual serial line is a chip, an integrated circuit on the board. And that is what actually that's the thing that's either in transmit mode or receive mode. It cannot flip instantaneously between them. For the sake of argument, on a very fast microcontroller, this will start sending data before, like in less amount of time than that. You can't assume that this will, that the chip will be ready to actually transmit data by the time the data starts coming in on that pin, and then you'll end up dropping bits and not all your data will get to the other end, which is not what you want. So what you do instead is between here you need to sleep, and then also between here you need to sleep. But how long do you sleep afterwards? Well, that depends, because the amount of time it takes to actually send out the data depends entirely on how much data there is to send. You could try to compute how much that is. So if you're sending at on a certain number of, like if your bit rate on your UART is a certain number of kilobaud, you could calculate exactly how long it'll take your chip to send 4 bytes of data. But a more reliable way of doing that would be that the API for controlling UART almost certainly has a function that is, am I currently still sending data? Like, is my send buffer empty or not? And so what you want to do here is, first of all, wait for it to be empty. So wait for it to finish sending the data, and then wait a little bit of extra time on top of that just to make sure that the chip has finished processing that data and actually sent it over the line before you drop it back into receive. This is great if you can just write sleep and like write a loop with no body that just continually calls UART dot not UART dot write buffer empty or something like that, and then asleep. But as we just discussed, we don't have that because of our callback setup. So these 3 stages, or potentially 4 stages, depending on how you structure it, need to be separate callbacks that are scheduled separately, and so forth. We can keep our first line. fact, we'll put that in a function we call, say, send begin. We need to send a certain number of data, a certain amount of data. We get the pointer to the block of data in memory that we're trying to send, and we get the length of the block of data. Now, first of all, regardless of what that is, actually we could have a short circuit. If length is 0, we don't need to do anything. Maybe if you want to handle that case, but we'll ignore that for now. First thing we want to do, we said, is we want to turn the direction pin on. So we have, maybe there's like set here 1 or something like that. We can assume that some function like that exists, and then we need to schedule something else to run after a certain amount of time, 1 microsecond, we say. First of all, the other function that we are scheduling to run, which I'm going to put on the left here, the other function that we're scheduling to run needs to conform to this function signature, right? It needs to, because it's being scheduled by the scheduler. So it needs to have 1 parameter, and that's a void pointer. How do we actually do that? Because we need to pass in sort of 2 pieces of information. We need to pass in the data and the length. Well, one way we could do that is to create a struct. For each parameter, it has a field. And then over here, we do our whole malloc thing, maybe cb for callback underscore data. So cb underscore data, we copy the parameter in, and the other parameter, the scheduling, send step 2. The data argument is cb underscore data, and the delay is, let's say it's already measured in, nanoseconds. We want to delay by 1 microsecond, which is 1,000 nanoseconds. Okay, and that's the entirety of this function. So what this will do is it'll turn on that direction pin, tell the scheduler to run this in 1 microsecond. And then 1 microsecond later, this will start. And first of all, we need to pull the actual useful struct out of that pointer, so we need to cast it back. And then maybe we do like UART dot send so we pass into our UART API. Again, exactly what that function looks like isn't important to us, but the data that we're sending and the length of that data, which is information it needs. After this, we're going to need to have something that loops through the scheduler, because we don't want to just have an infinite loop, because that won't let any other code run. So it loops through the scheduler, waiting for the UART circuit on the chip to finish sending out that data, and then turns off the direction pin a set amount of time after that happens. Does any of that code need the data or the length of the data that we're sending? No, right? All it needs is the UART, which for now we're assuming is a global variable. So that means we're now done with that data, and we can free it. So that frees the allocation made by malloc here. And now, send step 3. Still needs the void pointer, even though we aren't using it. It needs to have the same signature in order to fit in the function pointer. And all this will do is, so if UART dot empty, it'll schedule one thing, else we'll schedule something else, and we can fill that in later. And then all we need to do to schedule this is call the same schedule function. We don't care what the data parameter is, so we'll just put in null, and that actually we want to happen pretty well immediately. We can start checking it, so that we don't end up waiting too long. And so let's say our system will send out 1 byte more or less every 100 microseconds. So we're not going to check every microsecond to see if it's done sending 4 bytes, because if we're sending at least 1 byte, which we're assuming we are, it's going to take at least 100 microseconds. So we can have this, say, if it's not empty yet, so if it's not done sending, we're going to schedule itself. Again, don't care about the data parameter because we're not using it. Let's say every 100 microseconds, which is 100,000 nanoseconds. Whereas if it is done, we're saying, okay, we'll only wait 1 microsecond for before we pull dear low again. That's only 1,000 nanoseconds, and then that only leaves us with underscore end, which again needs that void pointer even though we're not using it. All it needs to do is set underscore dear 0 and call it a day. It doesn't need to schedule anything else because we're done sending. So, quick recap, we need to send. That involves turning on the direction pin to say we're transmitting, waiting a certain amount of time before we actually start sending the data, so that requires allocating some stuff on the heap, allocating enough memory to store that information that we need to pass on, copying it in, scheduling that to run, passing in that structure we just allocated, and then in 1 microsecond when that happens, we start sending the data, and we schedule it immediately to start checking the data, or checking to see if it's done sending, and then we check every 100 microseconds from then on. If it is, as soon as it is done, we can go to the end stage where we just turn the direction pin back off, but we have to wait a certain amount of time before we do that just to make sure it's done sending. And the actual time values would be based on the specific chip you're using, the specific microcontroller you're using, and all that. Okay, so I'll just go over a couple of things that this doesn't really take into account. One is error handling. So what if this fails? Any I/O operation, as a rule, could fail. UART could fail because maybe there's too much stuff in the buffer already, because, again, some other part of your program failed. You don't know why, but any part of this could fail. So what you probably have is, I didn't write void here, but this would have a return type void, but what you probably actually do is have another parameter, which is a function to call if there's an error. And then so if this fails, you just immediately call that function. If this fails, like if UART.send fails, well, then you need to call that function there, which means that you need to pass that function along what if setting the direction. Again, setting an output pin could fail. So that whole error handler function would need to be passed along through here. And you need to handle that case. And the other thing that you need to remember when handling it here is whether there's an error or not, you still need to free the memory.